right, last part of mechanics, and that's energy. So first thing we're going to do is we're going to define the different types of energy that we use, and then we'll go into conservation. So there are lots and lots and lots of types of energy, okay? But essentially, all forms of energy can be divided into two types. We get potential energy and we get kinetic energy. So potential energy is energy that an object has due to its position relative to another object or because it has stored energy. So things like electrical potential energy, potential nuclear energy, gravitational potential, chemical potential. So it's a stored energy that has the potential to do something. Kinetic energy is the energy an object has due to its motion, okay? And that motion could be translational, rotational, just moving forward. It's just that it's going to have some sort of velocity, okay? So it's got to be moving, okay? So if we look at gravitational potential energy is actually fairly straightforward, okay? And it's the energy an object has because of its position in a gravitational field relative to a reference point, whether that be the floor, the surface of a chair, a table. It just has to you have to compare it to something though. So the symbol is EP, E standing for energy, P standing for potential, and it's a subscript P. It's measured in joules because it's energy, and it's a scalar, which means it doesn't have a direction. The equation, which you have seen somewhere along the line, is EP equals mgh. EP is gravitational potential energy, M is mass in kilograms, G is gravitational acceleration, which is 9,8, so that's constant, and H is height. And before you ask, yes, you will be given these on your information sheet. Okay, so we have to have a reference level, a zero level, which you'll see when we do the examples. Whenever energy is transferred to an object, work is done. Okay, so we do work in the physics sense when we transfer energy. So for example, a crate has a mass of 100 kilograms. A crane is used to pick up the crate with a constant speed to a height of 5. I want the potential energy of the crate. Well, EP equals mgh, and that's when it gets to the top. It's 100 times 9,8 times 5, 4,900 joules. That's the potential energy that the crate has. So the crate is now here. So here's my crate. Okay. And it's 5 meters above the ground. So now it has a potential energy of 4,900 joules. It has the potential to do 4,900 joules of work. Okay? Another example, a crane lifts up a car with a mass of 1,000 kilograms at a constant speed to a height of 5 meters above its original height. Calculate the car's gain in potential. Well, it doesn't matter where the original height was according to the floor. The point here is that it only went 5 meters up. So when we look at the potential, it's now 49,000 joules. It was 10 times the mass, so it's 10 times the energy. Okay, so what does that mean? The relationship between an object's mass, potential energy, and height is the following. EP, this sign means directly proportional. Okay. So what that means for me is if I double the height, I'll double the potential. If I half the height, I'll half the potential. So potential depends on height, and whatever I do to height, potential will do the same. So if I double one, I double the other. Okay? Potential is also directly proportional to mass. If I double the mass, I will double the potential. If I halve the mass, I will halve the potential. So they increase and decrease by the same factor. Okay? So quickly, before you move on, do activity 1 on page 250, questions 3, 4, and 5. Pause the video, do them, come back. Okay? I'm now assuming you've paused the video and you've come back. Kinetic energy. Kinetic energy is the energy of an object that is the energy an object possesses as a result of its motion. So it's got to be moving. Now it's EK. K means kinetic. Subscript K. Measured in joules, just like potential. It's a scalar, so no direction. EK equals a half mv squared. Please don't forget the squared, and yes, this will be on your information sheet. You're going to forget to put the square. It's a problem, okay? So EK, kinetic energy, M mass, V velocity or speed. Okay, so an object that has a mass of 6 kilograms, M, is pushed along a smooth horizontal floor by a horizontal force of F. The object's velocity is 2 meters per second after it has covered the distance. I don't care whether it accelerates it or not. I just know that by the time it gets here, it's going at 2 meters per second. And I want to know what its kinetic energy is at that point. Well, EK equals a half mv squared. So that means it's going to be a half times 6 times 2 squared, 12 joules. Nice and simple. Okay? Not bad. Relationship between the object's mass, kinetic energy, and velocity. Well, EK is directly proportional to V squared. Okay, not V. Alright, so that means that when velocity doubles, EK will be 4 times bigger. Okay, it's the square of the velocity, not just velocity. But it is also directly proportional to mass. So if mass doubles, EP doubles. Okay, so look at an example. A trolley with a mass of 2 kilograms is at rest, a horizontal force of 100 newtons. So there's mass, there's a force is applied to the trolley, and it starts moving in the direction of the applied force at 4 meters per second. So at 4 meters per second, that's the velocity. They want kinetic energy. Well, EK equals a half mv squared. So half times 2 times 4 squared. Hopefully you can do this in your head, which is 16 joules. The force was irrelevant. It didn't matter. Okay? Didn't matter about the force. So, pause the video. Do activity 2, page 251, question 3, 4, 5, and 6. 3, 4, and 6. The memos will be on Teams. Okay? Let's go back to this and let's do the... we're now looking at exercise, just an extra exercise. So we have a crate of 890 kilograms. You might want to do activity 2 after this exercise. Okay, it's lifted to a height of 2.1 meters. Calculate the crate's gravitational potential energy. Well, I know the mass, I know the height, so it's simply just multiplying everything together. Remembering that G is 9,8. That's a constant. You need to remember that it is also given to you. The big number was a big mass. We're okay with that. Fairly straightforward. Okay? Question 2. Charmaine, 55 kilograms, jumps on a trampoline. She jumps to a height of 47 centimeters. What is her gravitational potential? This is in centimeters. Height can only be in meters. So, convert 2 meters. How do we convert 2 meters? We divide by 100. There's 100 meters, 100 centimeters in a meter. Straightforward, substitution, multiply it all out, we're all happy. Okay? George has a mass of 70 kilograms. He climbs the stairs to the science lab. Calculate his gravitational potential energy. Gravitational. This is 12 meters. I don't care about that. I care about his perpendicular height from the ground. So actually the 5 meters is the important part here. So EP equals mgh. So it's 70 times 9,8 times 5, which is 3,430 joules. Nice and simple. Okay, this is nice. A container has a gravitational potential. So now they're giving us EP. It's raised to 5 meters. So I know that EP is 1,150 joules. We know that the height is 5 meters. So we want mass. Well, EP equals mgh. 1,715, which will then equal to m times 9,8 times 5. So m is 35 kilograms. And I don't think I quite left you enough space. Oh, no, next question. So, 78,400,000 joules of gravitational potential energy, so that's EP, is transferred when an aeroplane lands. If the mass of the plane is 40,000 kilograms, how high was it? That's H before it started to land. It's exactly the same question as question 4 with bigger numbers. So EP equals mgh. 78,400,000 equal to 40,000 times 9,8 times H. So H is 200 meters. It wasn't very high, but it was very, very heavy. Calculate the kinetic energy of Caster Semenya, who runs at a constant speed of 4 meters per second, assuming she has a mass of 65. Well, it's kinetic energy. Well, EK equals a half mv squared. So it's a half times 65 times 4 squared for 520 joules. Her speed halves. Now what happens to her kinetic energy? It's not going to be half. Pay attention. If her speed halves, it's now 2. Her kinetic energy is now only 130. It's 4 times smaller because EK is directly proportional to V squared. Okay, so it's actually a half V squared. So it's a quarter. Very, very important. A wagon, 100 kilograms, is pulled across a smooth surface with a velocity of 8. What's the kinetic energy of the wagon? Well, EK equals a half mv squared. So it's a half times 100 times 8 squared, 3,200 joules. Not a problem. If a wagon with double the mass is pulled with the same speed, calculate the EK. Now, EK is directly proportional to mass. If I double the mass, then EK should be double. We should get 6,400. Okay? Oh, look, we got 6,400 because the mass is now 200. Now they say, if the velocity is halved, now we've just done one where it is halved, and then the EK was 4 times smaller. So if we halve the velocity, it's now going to be 4 squared. Oh, look, it is 4 times smaller than the original. That's 800 joules. 7.4. Now they double the velocity and they double the mass. So, double the mass, double the velocity. It's now 25,600. Do the calculations, okay? It's actually going to be 8 times bigger, but don't stress about that. Okay, nice and simple. Make sure you've got the concepts of EP and EK in your head, what we use where, because you're going to need that for Unit 13.